Next, we are going to discuss evolution problem. What is that? So here remember that the equations, whatever we have discussed, homogeneous or inhomogeneous, there the operator was time independent. Okay, the operator was not a function of time. Now, if operator is a function of time, then the notion, the way we are discussing that A generates a semi-group, etc., does not necessarily extend, correct? Because every time t, the A changes, correct? So we need a different settings, we need a new set of definitions, which should basically generalize the notion of semi-group. Okay, so like A, which is not a function of t, is a special case of this evolution problem where A is a function of t. So whatever we're going to introduce for that general class, if we restrict, we should get similar result what we have obtained for homogeneous or inhomogeneous initial value problem. Okay, so for this we need some definitions in the beginning. So we start with this definition. Let TT be a C0 semigroup with its infinitesimal generator, a subspace Y of X is called a admissible if it is an invariant subspace of the TT semigroup, and the restriction of the semigroup TT on the subspace Y is C0 semigroup in Y. Okay, so here a semigroup, a subspace Y would be called A admissible if it is invariant subspace of TT. That means TT of Y would belong into Y, correct? So it's invariant. So TT of Y does not leave the subspace Y. It does not go outside. So TT of X is of course inside X, but if we take a subspace of X or Y, it is not necessary that the image of TT and the image of those points, the subspace under TT, would also be in that subspace. But okay, so if we have such subspace Y, the image of Y under TT is inside Y for each and every T. Okay, and furthermore, if we also have that TT restricted on Y, okay, so that thing is a C0 semigroup in Y. Okay, so if we just restrict the, I mean, if you just consider the same Banach space norm on Y, so we get a non-linear space there. Y need not be a complete space in general. Okay, so a non-linear space there, and in that non-linear space, if this TT restricted Y is a C0 semigroup in Y. Okay, if that thing also is true, then we call Y as A admissible. Why A? Because TT is obtained from A only, correct? Because A is the generator, okay? A is the operator which appears in the Cauchy problem. From A, whatever the semigroup TT you have obtained, and then we are looking at the subspace of the Banach space X, which satisfies two conditions. One is that Y is invariant subspace of TT, and TT restricted on Y is the C0 semigroup in Y. Okay, so if both are true, then we call Y as A admissible. Okay, next, this is the definition of homogeneous evolution problem. So here consider d phi dt is equal to A of t phi t. Okay, so here it is homogeneous. Why? Because I do not have plus f. Okay, I do not have any data here. However, here the operator A is a function of time varying function. Okay, is a non-autonomous system. Okay, So we call this problem as evolution problem. Okay, we do not call it anymore initial value problem, although okay, so something, but here see, I mean, here for every time things are changing, so s need not be always 0. So small t belongs to s to capital T, s greater or equals to 0, sum s, and phi of s is equal to x. So at time s it is x, and then we are starting the equation. Okay, so we need here some more definition. So instead of semi-group, we are going to introduce this. We are going to use this two-parameter family of operators, where semi-group was a single parameter family of boundary linear operators on the 1-off space. Here, instead, we are going to take two-parameter family. One is the starting point, and another is the ending point. Okay, so UTS, okay, UTS, that is defined as phi of t, where phi is the solution of HEP. Okay, I will call this HEP because H for homogeneous, EP for evolution problem. Okay, UTS is equal to phi of t. Now this theorem we quote here. So let AT is a bound linear operator for each and every t. Okay, so this is a very special case. Okay, a very restrictive case, which we actually have visited earlier for the initial value problem. When A is bound linear operator, then it generates a uniformly continuous semi-group, and that is can also be written as e to the power of t times A, correct? And then the solution of this thing is also very clear. It was just e to the semi-group itself. So, but here for this case, if A is a time varying operator, A of t is BLX, okay, for each t, and then t to AT is also assumed to be continuous. Okay, both of these conditions are assumed. Then for each and every x, small x and capital X, as before, because before also we could assure existence of classical solution even if small x is not in the domain of A. But here actually for matrices, etc., the domain which are bounded linear operator, so their domain is in the full thing, correct? And so then for all x in capital X, the homogeneous evolution problem has a unique classical solution. Okay, now we introduce this evolution system from U. Okay, a two-parameter family of bound linear operators. So here it is just a particular cooking up, but we are going to find out, not a particular example, but we need to discuss that when should we call a two-parameter family of operators as evolution system. So these are the properties. A two-parameter family of bound linear operators UTS, where S and T is between 0 to capital T on X, is called an evolution system, or ES, if following both hold. What first is that USS is equal to I, okay, and UTR composition URS is equal to UTS. Okay, so let us take some particular subclass where we can actually justify these relations. So imagine that if AT was a very special, it was independent of time t. Okay, so then this would give me that capital T of t minus s. Okay, capital T of t minus s. Okay, and then if you have that UTS is equal to capital T of t minus s, then USS is capital T of s minus s. S minus s is 0, so capital T of 0 is equal to identity, so USS is the identity. So in the case where S U T R, I mean UTS is equal to T capital T of T minus S for where T is a C0 semigroup, then this can also be justified. Here U of T comma R is capital T of T minus R, and then U of R comma S is capital T of R minus S. So here we have capital T of T minus R. Here we have capital T of R minus S. Then using the semigroup property, you are going to get capital T of T minus R plus R minus S, that is capital T of T minus S. But capital T of T minus S is U of T comma S. Okay, you can justify this also for this very special case where UTS is capital T of T minus S for some semigroup capital T. But that is a very special case. All the evolution system need not have such kind of representation. Okay. Second thing is that as a function of T and S, TS to UTS is strongly continuous. What is the meaning of strongly continuous? That means that if I have UTS X, where X is coming from the Banach space, so then this function, this map, here left hand side I have the product space time in S, TS, and right hand side I have Banach space UTS X, and there we have the Banach space norm. So if that map is continuous, okay, then we call this map is strongly continuous. So under these two conditions, if you satisfy these two conditions, then you call U as a evolution system. Now we state this equation. So d phi dt is equal to at phi t, this thing. Okay. So here it is inhomogeneous. So remember, here we do not have f here. Okay, so therefore it is homogeneous evolution problem. Now we state inhomogeneous version of that. Okay, inhomogeneous evolution problem. Okay, so we consider d phi dt is equal to at psi t. Oh, sorry, here it should be phi. So same phi here, both the sides. D phi dt is equal to at phi t plus f of t for all t in S to capital T close, and phi of S is equal to x. So here I have inhomogeneity. So where f as before is an integrable function, f is in L1. So in this time interval S, because S is the starting point here, S to capital T, okay, so S to capital T to X, it is in L1, and assume that there exists an evolution system associated with the family of operators AT. Earlier, for initial value problem, we had only one single operator A, but now we have a family of operators A, because A is itself a function of T. And now for this family of operators, if we assume there exists an evolution system, okay, so what is the meaning of associated with AT, that thing? That means that there exists one evolution system U such that for which when we take the derivative, we are going to get A times U. Okay, we are going to show in the next lecture the detailed definition of this, that when we should call a evolution system is associated with AT. Okay, the function phi, which is continuous function cst to x, given by phi t is equal to utsx plus integration s to t utr fr dr. Okay, so this is called the mild or the generalized solution to the inhomogeneous evolution problem. So earlier case, the uts, okay, utsx, so here say utsx appears. So uts x is the so x is missing here, so UTS-X is the mild solution of this equation. Okay, so next we would study when can we associate an evolution system with a given family of operators AT. Okay, so as earlier we had A in the homogeneous or inhomogeneous initial value problem, and then Hill-Yoshida theorem could assure for certain cases that we can actually associate a C0 semigroup there, and when we can associate that C0 semigroup capital T was very useful to write down the solution of those Cauchy problems. Here also I have, instead of a single operator A, I have a time dependent family of A, and for that we would also have a proper notion of evolution system, and then only thing is that when under what sufficient condition on A we can assure that we can associate one evolution system. Why is that question interesting? Because if we can do that, then using that evolution system we can write down this extension of formula of variations of constant to write down a mild solution of the equation. Okay, and under some strong conditions on X and F, etc., one can assure existence of classical solution also. Okay, so let me stop here now. Thank you very much.